on the effectiveness of vision transformers for zero-shot phase anti-spoofing. This work was done by Anjit George and Sebastian Marcel from IDIAP Research Institute, Martigny, Switzerland. The issue we are addressing is the vulnerability of face recognition systems against presentation attacks. Presentation attack detection or anti-spoofing is essentially countermeasures against presentation attacks. Here, you can see some of the presentation attacks using 3D masks and various other types of attacks. Though there have been many works in literature, the existing PID methods do not generalize well in unseen attack and cross-database scenarios, which severely limit the application of face recognition systems in safety-critical scenarios. The main challenge with PID methods is that since the difference between bona fide and spoof samples are minute, typical CNN-based PID methods have a tendency to overfit to the nuances in the training datasets rather than focusing on the actual spoof cues. This results in poor generalization. Essentially, the PID method need to be robust against unseen attacks and environments to deploy in real-world scenarios. In this work, we propose a transfer learning-based approach using the recently proposed vision transformer model for PID. The pre-trained VIT model provides a good prior which reduces the overfitting and obviates the requirements to train the model from scratch. The transformer architecture is becoming very popular in deep learning pipelines across different modalities such as speech, NLP, and now vision. Recent work, specifically the one shown below, has shown that the transformers can replace convolutions. The vision transform model are a straightforward extension of transformers to computer vision. The transform model is used to replace convolutions in a deep neural network. The VIT model can integrate information from wall images in the initial layers itself, different from CNNs. The transform model does not have typical inductive bias of convolutions, such as translation, equivariance, and locality. Basically, in the vision transformers, the image is divided into patches, and each of them is projected into a high-dimensional vector space, and these embeddings of these patches are considered as the sequence input to a standard transformer. Now, the wall image can be represented as a sequence of these vectors. A classification token is also prepended with this sequence. To add a notion of position or adjacency in these vectors, a learnable position encoding is also added. After this, we pass the sequence through several transformer layers. The representation from the last transformer layer is taken as the embedding vector. Now, for the PID task, a single fully connected layer with one node is added, followed by fine-tuning the wall network. Like most of the other vision models, we can do transfer learning with these models as well. We show the diagram of our approach here in the figure. We used the pre-trained model and added a fully connected layer on top of 4 binary classification. The model is then retrained end-to-end for the PID task under different settings. At the input side, face images are aligned, cropped, and divided into patches as the input to the network. We have performed experiments with zero-shot protocols in both HQWMCA and SIWM datasets. Both the datasets contain a wide variety of attacks. We limit this analysis to RGB channel alone. We report the average classification error rate, ACER, and HTR in these datasets. There are different ways to use a pre-trained model for our task. We have evaluated 3 different cases for the VIT architecture. We transfers FC. Here, only the last fully connected layer is retrained and all the other layers are frozen. This corresponds to the fine-tuning scenario from a pre-trained model. We transfers all layers. All the layers from the architecture are adapted during training. We transfers E plus FC. Here both the first embedding layers as well as the final fully connected layers are adapted during training. From the table, it can be seen that for unseen attack detection, adapting the fully connected layer alone leads to great improvements compared to state of the art. It seems the representation from this model is very good to model the normal appearance of face. The results in HQWMCA datasets are shown below. Compared to the baselines, the proposed method achieves much better performance just by adapting the last layer. The figure shows the attribution using LRP maps. It can be seen that the VIT model correctly focuses on the relevant region for the classification. Similarly, the VIT model achieves much better performance in SIWM dataset as well. From these results, it is clear that the VIT model outperformed typical CNN-based PID methods by a large margin. Here we show the t-SNE plot of the representation from the pre-trained VIT model for both these datasets. It can be seen that the features already show some discriminative information. Again, to evaluate the generalization capability of these features, we have performed cross-database experiments across these 2 datasets. It can be seen that these models outperformed other baselines by a large margin. We also show the comparison of complexity of the VIT model. Currently, the parameter and computational complexity of VIT models are very high compared to other baselines. However, it is possible to optimize the models for PID task. To summarize, the representation from the pre-trained model is very robust in terms of modeling natural images, meaning visually imperfect attacks are easily detected by VTransfers. Specifically for the PID task, VTransfers works very well for PID in both unseen and cross-database settings, which are the most challenging issues in PID. Now, coming to the limitations, one of the main limitations is the higher computational and parameter complexity. Small models can be developed as future work. Another limitation is the poor performance in case of very realistic 2D images, as the model uses only RGB channels. The source code will be available in the following link. This work was funded by IRPA Battle Project and we would like to acknowledge their support. Thank you for your attention.